Okay, hello everyone. Today is the last talk of the seminar series on derived algebraic geometry. So today we will hear about derived, what is the specific topic? Oh, derived symplectic geometry. Okay. Oh,
Yeah, I will just mention several topics.
okay, I have it slightly different
Yeah, I
here.
mean, I will essentially outline what we call PTVV symplectic geometry. PTVV's symplectic geometry. So I will just mention essential ideas, definitions, some results from literature.
Okay, perfect. Thanks.
Hmm? Okay, so let me remind you some just notation. So if you recall, for any x, let's say x is a derived stack for any derived stack x. So when we say derived stack, what should we understand? So by which we mean actually the following, very roughly speaking. So you should understand a kind of a functor, right? An assignment like this for each CDGA, right? This is our local model. And this functor can be also identified with the mapping space from spec A to X itself. Okay, this is kind of a Yoneda lemma argument. So therefore, when we say derived stack, I mean, you should understand a kind of a collection of charts. Okay, just very similar to the manifold usual Diffgale. So we have collection of charts like this. Okay, and also let's say when we consider function, right? Regular function on spec A, it will give you A itself, right? And also what else? When you consider quasi-coherent sheaves on spec A, it will give you A modules. Okay, so this is our local picture, and you can actually glue them. There is some kind of a limit definition, if you remember. So therefore, we can define for such objects, we can define some standard notions like algebra of functions on X using limit, right? Limit in infinite categories. You can define OX. You can define very particular sheaves, right? Quasi-coherent sheaves on X. And essentially, you can define Deram X, okay? Deram algebra, which will be the main object in this lecture. And what was it? So let me tell you. But for simplicity, let's work with the affine case. Let's say we have a drive affine scheme. Okay. So for this thing, deram spec A, I mean, we just write deram A, and by definition, this is just something like this. Or maybe I should say something more. Let's also assume this A is sufficiently nice. Okay. So if you remember, we also have a notion like standard form CDGAs. So we assume A is sufficiently nice. So formally speaking, we are just considering a cofibrant object in that category, whatever it means. But these are nice objects. So for instance, if you consider standard form CDGAs, and if you remember, one nice advantage of using this, when you consider the cotangent complex, you can actually identify this cotangent complex with the A module of Kähler differentials. So usually this is not true for arbitrary A. Therefore, just forget the technicalities. We always identify cotangent complex with the module of Kähler differentials. Therefore, this is nothing but the symmetric algebra over A of this omega A shifted by 1. Okay. And if you write it more, if you want to write this thing more clearly, it turns out to be you have some grading Okay, you have this exterior product of this omega 1a. We have some shift p, so because of this symmetrization, and so we have p greater than 0. So this is what we should understand when we consider theorem A. But this thing itself has a grading, therefore this turns out to be a kind of a double complex. Okay, so we have actually something like this, some internal grading like this, p positive 1 and a negative 1. Okay, so therefore this is a double complex actually. This guy turns out to be a double complex with the total differential d total d plus d deram. And as you may guess, d deram, acts on this p. So p is what we called weight, and this n what we called degree. Okay, so therefore deram differential increase weight by 1. Similarly, internal differential d increases degree by 1. Now we have definitions. So this is what we call Deram algebra. Okay. So therefore, as you may guess, if you want to define P forms are just particular elements of that double complex. Okay. So when we say P form by a P form of degree n, okay, this is the terminology, or sometimes we say n shifted P form. Okay, on X, but don't forget X is always affine. So let me use notation omega P on X. So we mean the following actually. We mean this omega P is actually the element of this double complex. Okay, like this. Okay, but we are not done yet. We want this thing to define a cohomology class, so such that d omega p is 0. Okay, with respect to the internal differential. Be careful, not theorem, but internal differential. So it actually means we have a cohomology class, right? Omega p is in here over X of this complex with respect to the differential. If you want, it's one of them is kind of horizontal differential, right? So we have a kind of a double complex structure like this. Arrows goes like this, right? The other arrows goes like that. And of course, there are compatibility conditions, which I didn't write down. Of course, these are all square zero, right? And there is some anti-commutativity relation. So something like this, okay? And this also, you can identify this thing by just using this shift. There is a shift here. So therefore, these two are also the same things. Okay? A, B. If you want to get rid of this shift, okay, also you have this kind of cohomology class. So therefore, for such element, we say its cohomological degree is n minus p. So its cohomological degree n minus p. Its weight p. Okay. So this is how we should read this notation and this definition. Okay? When you have an n-shifted p form, we also mean you have a cohomological degree n minus p and weight p element.
N minus p there. How is this cohomology defined?
Cohomology of this complex with respect to the internal differential. Only the which means we are just considering, I don't know, it depends on your perspective, let's say the horizontal differential. Okay, let's say the horizontal one's d, the other ones the deram. Okay. Good. And we denote the space of such, okay, space of such elements by, so let's say the space.
So sorry, the underlying chain complex here, is it the sum of the diagonals or sum of the what is the underlying chain complex?
If you choose D like this, in that case, the horizontal ones. Okay.
But are you
so D, maybe I should.
In a fixed level.
In a fixed level, yeah.
In a fixed degree, what is
Yeah.
the chain complex? Is the sum of the poles?
I mean, yeah, I mean, just one row, yeah.
Are we taking one row?
So D increases N. Yeah, I mean, yeah. Maybe I should have written in a more detail, but so these are some, this increases N by 1. In that direction, you are increasing P.
Oh.
Okay. I mean, to save time, I didn't write down everything, but good. Be good. Okay. Let's say, okay, the space of such elements. Another notation, we are using this curly A. So the weight is here, our base space is here, and our degree written here. Okay, so we use this notation. And maybe I should make a remark, an important remark here. So actually, this is from another important result from PTVV. Actually, PTVV shows that this thing is actually a simplicial set. Okay, it shows two things. This is simplicial set. This is the first thing, and the second thing, if you let this x to be free variable, I think I mean a simplicial set. Yeah. Yeah, I'm not sure, so I have to think about it. Yeah. And this thing is a stack. Okay. So therefore, this is a kind of an assignment for each CDGA. It assigns a simplicial set. Okay. So it's like a, you remember the definition of a derived stack. Okay. This guy is a simplicial set or infinite groupoids, if you remember. So this is how actually. So I skip these technical details. Remember, we start with the affine case, but of course, somehow you need to glue them, right? To define everything for arbitrary x, because in these things we are using affine case. So actually, what they did, they just prove these things, and then these things imply that actually you can make these definitions for any x. Huh.
Okay, so is that thing a subset of the hn minus 2? Is it like WP that satisfies WP0?
Yeah, actually, yeah, this is just some omegas like this satisfying this property.
So it's APXN.
Uh-huh.
Each degree is a set, and then your the simplicial set is which degree? Is it n or p? N?
Degree n, weight p elements.
So it's a simplicial set where the n degrees, the n simplices are given by these APXNs. That's
AP. So yeah, I think you yeah, I think so. Yeah. Mm-hmm.
but I'm still confused is all right.
Mhm.
Here we have D, which is okay. So is it possible to label what is N on this double complex?
So let me.
So I was thinking if you have a double complex, you can take the diagonals to get like out or something.
Yeah, you're
And
right.
that would be
You're right.
the diagonal would be the N. That's how you're thinking.
So
Like
here,
this, if you want.
so let's say this one is the part N. Okay. So this part is a N plus 1. Okay. And in that direction, this part is P plus 1 omega 1, but degree N. And this one, P plus 1 omega 1a, but degree N plus 1.
Okay, but then the simplicial set is in degree P, right? The P is the variable here that goes between, because you have to now, you already use D, which goes from left to right.
Yeah.
Define a cohomology. For the simplicial direction here, I'm using the other direction.
For the other direction will come, will enter the picture when we define closed forms. Okay, this is only for P forms of degree N.
So I'm just trying to understand.
Mm-hmm.
So the simplicial set over there, which is you said APXN, is this the peak level or is this the end level of the simplicial set?
Oh, I see.
That's what confused me because you already used D, which changes from between
here.
columns, right? I guess
Yeah.
the
These are the Derived parts. Let's say these are the D1s, and you have this all of these properties. Okay.
Yeah, so that's why I'm confused. N or the P is the degree there.
I see. Yeah,
so for example,
I see.
What's the face of WP? What's the degeneracy of WP?
What is it? Oh, you want to think like this? Yeah. Yeah. So you want to see the face and degeneracy and everything. I see. Yeah, actually, I don't know in that case because I just want to see them like an element of this double complex, satisfying this D0 property. I mean, I really don't that much interested in the simplicial set structure of this guy. So this is just some kind of technical remark about how they prove it.
But I guess that we have to go to simplicial affinity groups.
I think so. I don't know how they did it. So just for some advanced remark, eventually this assignment turns out to be a derived stack. So this is how they pass from affine case to the arbitrary x. This is what I'm just trying to tell you. But you're right. I mean, maybe we need to discuss it in more detail here. So another nice definition, when we define these two things are the same, for instance, what if you choose two such forms, omega p and omega p prime, okay? Let's say we have some degree weight x degree n forms, and we say they are equivalent, okay? So if and only if there exists some element alpha p, but it is now in, I mean, exactly the same weight, but one less degree, okay? So degree is one less, such that their difference is just d alpha p, okay? And such alpha, it turns out to be what we call path, okay? Path in this simplicial set, okay? Joining these two things, okay? And also, maybe one more remark here, I forgot to tell you here. So when you have this kind of interpretation, and if you look at the pi zero of this thing, okay, connected components, and then the connected components turns out to be the n cohomology classes like this. Okay, so that this is our relation. Hn. Okay, something like this. So another terminology. So of course, once you have this omega 1a, so when you look at the dual, this is how we define the tangent complex. Okay. Actually, we are cheating a little bit. Remember, we are using this nice CDGAs. So implicitly, we are using this identification. So this is how we define our tangent complex. Okay. And this is just home A omega 1a. So these are the maps like this. And if you remember, I don't know, in previous lectures, we discussed the identification. This is how we identify derivations. Okay, derivations A. And remember, derivations are our vector fields. Okay, so this is analogous to the classical construction. So you can just consider the elements of the tangent complex as certain derivations. Okay? So this is our tangent complex. Okay, we have a cotangent complex here. And we define the notion of a non-degeneracy. So first of all, any two form of degree n, okay? So let's say omega p. So any such form induces the following map. So omega p, let me use this notation, from Ta to omega 1a shifted by n. This is by using contraction. Okay? So via iota map. Okay? So therefore, there is a nice, let's say, the antisymmetric morphism, very similar to the classical case. Okay? Remember, in the classical case, when you have a true form, right? So you can define a map like this between the tangent bundle and the cotangent bundle, right? In the classical geometry. But now you can actually establish a kind of a morphism between these two complexes. But there is some shift. And this leads to the following definition. So another definition. We call two forms, such two form non-degenerate. Sorry, we can discuss degeneracy condition. So two form omega p is non-degenerate. Okay, if this map is an equivalence, okay, weak equivalence, and in that case, the weak equivalences are quasi-isomorphisms. Okay, the induced map. Okay, this one is a quasi-isomorphism. Okay. Good. So if you remember the usual symplectic geometry, we also have a non-degeneracy condition of a two form, right? In that case, we require isomorphism between two bundles. Okay. But what is the missing data? So if you want to define symplectic structure, you need the notion of a closed P form. Okay, closeness. So remember, in this definition, we also have a closeness condition here, but the actual closed P forms will require closeness with respect to this differential, okay, d total, not the internal ones. So we have the following definition. So by a closed, okay, P form of degree n, okay, on X. So we mean the following. We mean actually not just one element like this. Instead, we require elements sitting on the diagonal. Okay, a kind of a formal sum, formal series. We mean a formal series, and we use notation like this: omega p plus 1, omega p plus 2, and it goes like this. Okay. Such that now the total omega is 0. Okay. So let me explain what's happening here. It's a kind of a cryptic definition. So it basically tells you that, i.e., so you have a sequence of elements like this, okay, not just one element like that, and you understand the notation. Actually, as you see, omega p sits here as a leading element. So we are just saying each such element, p plus I, will be in this part of the complex. Okay, n minus I for I positive. And if you just chase the diagram, you will see that all of these things will sit on the diagonal because you want closeness with respect to d total. And also this condition, d plus d deram, this is your d total, omega 0, this splits according to the weights. So how it splits? The first condition, so there are infinitely many relations here. So let me write it down a few. First one will be something like this. And the second one will be something like that. Okay? And it goes like this. So what is happening here? If you look at carefully, without this term, this is deram closeness. But with this term appear, if you look at carefully, what is the degree of this one? One less, which means that this is almost the deram closed, but up to a path, up to a homotopy. Okay, so therefore it's like kind of a deram closeness up to homotopy, up to homotopies. Okay, so you have kind of a D closeness and plus deram closeness, but it's a kind of a coherent sense. So it's like always up to homotopy. So therefore we sometimes say, I mean it's a formal, another maybe terminology. The first term, if you look at first term, so it will be inside here, right? When I is 0, put I is 0 here. So which is exactly here, right? And because of the first condition, this guy is actually an honest p form of degree n. Okay? Honest p form of degree n. So therefore, here is the idea. You have a leading term. Leading term. Formally, we call it leading term. And you have a correction terms. Okay? Homotopies. Okay? Homotopy correction terms. So this is how you define a closed P form. This is close up to kind of deram coherences. These are corrections. Correction terms. So good. So this is kind of important. So let me maybe let me tell you using this cohomology classes. Actually, you can see that. So let me maybe if I have some place here, let me write it down here and then So if you look at carefully, you can easily see that such omega will be in the following cohomology. Instead of just some single complex, you consider all possibilities because you are considering infinite series like this. So therefore P plus I, okay, 1I, so there will be some shift. I mean, you can check it, maybe it looks complicated, but, and with respect to D total, okay? So therefore they also, such element also define a suitable cohomology class. Okay? So therefore we will have similar interpretations like that. Now we will define space of such elements. So I'm going to use very similar notation. Okay. So the notation for such elements, so space of such elements, we are going to use P close Xn. Okay, and it satisfies very similar properties. It's a simplicial set. If you have free property here, you have derived stack, and also if you look at the connected components, it will give you this cohomology classes. Okay. Okay, so let's make a quick observation. So any questions so far? Maybe before that. Okay, good. So the first natural observation is you can easily see the relation between these two. This space, so there is a actually there exists a map, there exists natural morphism between this space and that one, right? There is a natural map. It essentially just sends, so you have omega, it maps to omega p, its leading term. Okay, there is a nice projection map, projection onto its leading term, onto its leading. Oh, good. So therefore, we have finally the following definition. By an n-shifted symplectic form or symplectic structure on X, we mean the following. We have a two form, as you may guess. We have a two form. Sorry, we have a closed two form. Okay, we have some omega, which is a closed two form of degree n. Okay, and such that its leading term is non-degenerate. Okay, remember, its leading term turns out to be just a two form of degree n, and we require it to be a non-degenerate, such that its leading term non-degenerate. So therefore, if you have a closed two form, you consider its leading term and you consider the induced map between cotangent and tangent complexes, and you require this map to be a quasi-isomorphism. Okay, I mean this is just very similar to the ordinary geometry, right? In ordinary geometry, you require a closed two form, right? But in ordinary geometry, you don't have this internal differential. You only have Derived differential, right? So therefore, D total turns out to be just D Derived. Okay? Because D is always zero actually. So there is no such. I mean, you should view this argument like this. In classical geometry, we actually have D, but D is always zero because there is no grading. Right? So you have a trivial differential. Therefore, D total reduces to D usual D Derived. Okay. So if you want, let me make the following remark. Okay, this is n-shifted symplectic form, and bunch of remarks, and I will show you an example, a simple construction. So maybe we should recall the classical setup. Classically, if you remember, when we say, for instance, a form, a P form, so P form, for a P form, we mean the following. We actually consider the section of the exterior power of the cotangent bundle, right? So the P form, any P form is just a section. Let's say this M is a usual smooth manifold. Okay? When you have a smooth manifold, you have a cotangent bundle, and you consider the P exterior power, and this is how you choose your P form. So P form is just the element of this one, and if you use this cohomological stuff, this is just H0 of this bundle, actually. Right? This is how you define sections. So therefore, P forms are just like zero cohomology classes. But in our case, in derived case, we just allow higher non-trivial cohomology classes. This is more or less the difference. This is the first remark. And the second remark, therefore, every P form, when you have a smooth base, is just zero shifted, okay, according to this language. So therefore, it's kind of non-zero cohomology classes kind of measures, I don't know, how far you are away from smoothness. Okay, when you have a smooth base, you only allow to have zero shifted P forms. Okay, but there are still non-trivial zero shifted P forms coming from a non-smooth base. For instance, you may have a scheme. Okay, you may have a stack. Well, this is the extension actually from classical case to the derived case. So the second remark, we also have a similar kind of characterization of these things. So you can really view the elements as a section of certain complex, certain quasi-coherent sheaf actually. So again, PTVV, Pantev, Toen, Vekuen, Vezozi, if you look at their paper, they showed the following characterization of the P forms, n-shifted P forms. They really behave as expected. Let's say they are like mapping space, quasi-coherent sheaves from OX, exterior product of LX shifted by N. Okay? And this is nothing but the right-hand side. If you know a little bit, sheaf theory, this is nothing but the global sections of this quasi-coherent sheaf. Okay? Therefore, similar kind of characterization So in terms of global sections, this is also possible in this derived case. But for the closed P-forms, there is no such thing. It's a little bit hard to characterize closed P-forms, but P-forms can be characterized in a very similar way as we already have for the smooth setup. Okay, it's just a global section of this quasi-coherent sheaf. And as you see, I just use Lx instead of this omega in this particular case because they prove this kind of identification for arbitrary derived stack. Okay, good. So let me show you a prototype construction. So what kind of form you should expect to see when we have n-shifted symplectic form. Okay. Çok geç hocam. Kaçta başladık ya?
Sanki 5 dakika geç başladık.
Tamam. Okay, okay. So let's at least see the following explicit construction. Let's say n is minus 3. Okay, let's say n is minus 3. Let me explicitly write down A. So define A, but just as a commutative graded K-algebra. As a commutative graded K-algebra. Okay, which means that I'm not defining the differential yet. Okay, and this turns out to be let's say a free algebra over let's say some K algebra A0. A0 is some given K algebra, just a commutative K algebra. Let's say with generators x1 0 xm0 0. Okay, generated by and free algebra over A0 generated by the following variables. We have variables in -1 degree and variables in -2 and -3. Okay, let's say A is a free algebra over A0, so therefore A is like you have a graded polynomial. Okay, you have A0 and you have these variables x1s, y minus 2s and y minus 3s. Okay, you have a free algebra over A0. Let's say this is our CDGA. But what is D here? Let us define D. And also in particular, this is how we define standard form graded algebras. Okay, standard form graded algebras are just written in that form. So we particularly constructing a standard form CDGA.
Why do you stop at 3?
Just in this example. So let us use n equals -3. So I'm just going to construct -3 shifted symplectic form, just to see. I mean, this could be done for any n actually. Also similar for any odd n. Okay, for even n, you need to be a little bit careful because, as you may guess, for even, for instance, when this is just -2. Okay, maybe before that, we'll see how to write down the form and we will understand why you need to be careful when n is odd or even. And the differential d is defined like this. First of all, dA0 is 0. Okay. And secondly, dx minus ij will be defined like this. There is a very particular element, what we call h. I will explain what it is. And the other labels, maybe I should minus 3 minus I. Okay, let me write it explicitly. Okay, let's define this like that. And we have other two, d minus 2j. It is just del h del x minus 1j. Okay, something like this. And where h is an element in a2, a minus 2, such that it satisfies the following property, what we call classical master equation. Okay, so h is called Hamiltonian. Okay, and we assume h satisfies this relation, and j from 1 to m1 is 0. Okay, this is what we called classical master equation. So there are some classical mechanical motivations behind these terminologies, but why we are assuming this? Because we are not done yet. So we propose some assignments. Now you need to check, of course, one can show that d square is 0. Okay, under this assumption, you can show this, and therefore it defines this pair. Now this is our CDGA. Okay, so therefore somehow you need to show that d square is 0, and along the way, so if you want, you can check. Along the way, you are going to use this property. So there is a not just some arbitrary assumption to make everything work smoothly. And then another paper by Berktav, Bussy, and Joyce. They show the following. Using this d above, they show that actually, before that, sorry about that. So first we define an element, omega minus 3. Remember our notation, we are using omega p. Now we want to construct minus 3 shifted symplectic form. So this is defined to be a very particular element, like this, e running from 0 to 1, and j 1 to mi, and d deram x minus ij, and the d deram y minus 3 plus I j. Okay, let's define an element like this. This is in particular in this part of the double complex. Okay, and if you want, you can write down, because I is only takes the value 0 and 1, so it runs from j d deram x0 j and d deram y minus 3j plus another summation d deram x minus 1 j d deram y minus 2j. So as you see, there is two possibilities to obtain degree minus 3 element. Either you use bottom degree here or top degree here, or you use kind of intermediate degrees. But when the number is odd, non-odd, so when the number is even, you can produce the degree by just multiplying elements from the same degrees. So therefore, you need to be a little bit careful. There are some middle degree elements. So this is how we can obtain an element like this. And now they show the following. They show that actually, so they showed the following. First of all, d omega minus 3 is 0. Okay, so therefore you should show that this is actually a honest minus 3 form. Okay, because this one is clear. There's no problem here. And secondly, so they also show that the element written like this, okay, all others are just 0, and you only have an honest minus 3 form here.
W minus 3 is always 0, even if a 0 is not 3.
You mean this one?
Like, you didn't say a 0 is 3. You just said it's coefficient A algebra generated by
Yeah, this is.
element. So it's not, it doesn't have to be necessarily the 3.
Yeah. In that case, we also take this thing like a still freely generated by these things. But one can always make that choice. So this is the kind
So
of.
for this 0, do you need that, or for the first?
But I guess because you need to apply d to here, so you need to use these definitions. Yeah, along the way you are just going to use this when you apply d. So using this anti-commutativity property, at some point you are applying d here, so there will be 0 contribution from that part. Yeah, straightforward computation. I mean, not that much hard. And because of these nice choices, so terms will cancel each other. So it's just a straightforward computation. But the most important part is they prove that any given n-shifted symplectic structure locally looks like that. So this is the Darboux theorem. So this is the reason you can always, they prove that you can always make these choices, and eventually your shifted symplectic form will simply look like this. Okay, this is therefore an important prototype construction. Okay, so this thing defines just closed minus 3 shifted 2 form. So they prove that, and eventually,
Some kind of rigidification.
yeah, rigidification, you're right. And what they call Darboux-like theorem. So you can find a very nice chart, let's say, which means that you can really simplify this A. Maybe you find a chart, spec A prime, but using localizations, you can really make this thing behave nicely, and you end up with a nice CDGA in that form, freely generated. So this is actually what they proved. Okay.
Is always enough, or is still an example? I mean, for
You mean
this
minus
theorem,
3?
For this theorem, you said you can always find a chart so that
Yeah.
it works.
Yeah.
So trio is always enough for this, or do you need higher, maybe 5?
In that example, it will be true for any n, for any given n. You give me just any n shifted symplectic, not necessarily 3, 4, 5, it doesn't matter. Even for 1, yeah. No, negative ones. As long as you have negative shifts, they give you the model. But this is, I mean, as I just told you, the model depends on the parity actually. So there are some 4 possibilities, either odd or even. But even for the even case, you consider n minus 2 even or odd. So there are kind of different models. I mean, modulo 4. So modulo 4, there are some 4 possibilities. So depending on your shifts, but more or less they will look like the same, but some additional terms will appear here, but the constructions are more or less the same. Yeah, n equals 0. Okay, and n equals 0 is exactly you only have usual dp dq, usual theorem. Yeah, usual theorem, usual symplectic geometry Darboux theorem. But now, if you are away from smoothness, what they prove, you have some kind of shifted structure because you are away from smoothness. But even if you have non-smooth base, you have a similar kind of constructions. Okay? This is the logic. And also they prove, so let me finish this. And also they prove that this thing is a quasi-isomorphism. So therefore, eventually, this implies this omega defines -3 shifted symplectic structure on spec A. Okay, we consider the corresponding spec A, of course. Okay, so as I just told you, maybe some closing remarks. So I was planning to discuss more examples and applications, but yeah, and this leads a Darboux type theorem. Let me just say like this. Theorem for any n negative. Okay? But of course, as I just told you, depending on the parity, your model will look like a little bit different, but construction will be the same. But of course, since I don't have that much time, let me briefly just say some words. There are very nice results due to many other authors, Brau, Bossi, Joyce, or Safronov. There are many nice results extending the classical symplectic results from classical symplectic geometry. I don't know, for instance, the Lagrangian neighborhood theorem. So there is a Lagrangian structure in that setup as well, which I didn't define, but it could be done. There are nice existence results from PTVV paper, like Lagrangian intersection theorem, studying critical locus of a function. It turns out to be, if you want to understand critical locus of a function, of a regular function, this guy turns out to be -1 shifted symplectic derived stack. This is just a corollary of the Lagrangian intersection theorem. So there are what we call AKSC construction, which is about the mapping space. So how to construct a symplectic structure on this mapping space, for instance, how to ensure the existence of a symplectic structure on that thing. And it turns out to be you end up with a shifted symplectic structure. So there are many nice existence results from PTVV paper. And if you want to see some applications like local structure theory, like this, you should look at papers of, I don't know, Joyce, Bossi, Brau, or Safronov. Maybe I should add some. And there are other applications to certain moduli problems. So these are the actually important examples. I don't know. So if you want to understand some moduli stack of quasi-coherent sheaves over some Calabi-Yau manifold, it turns out to be some shifted symplectic derived stack. So there are very nice, so I was planning to mention them, but I don't have that much time. So there are nice applications to certain moduli problems. There are nice existence results coming from PTVV, and there are results regarding this local structure theory. Okay, so these are maybe some last remarks. Maybe one more remark, what we did. So we also have some work in that direction. We also mimic this procedure to introduce shifted contact structures. Okay, and then we also produce certain examples very similar to this local structure theory, Darboux theorem for shifted contact structures, symplectifications for shifted contact structures, Legendrians For instance, if you know classical contact geometry, so there is a nice dictionary between symplectic geometry and contact geometry. We just extend this dictionary to the case of derived, let's say, context. This is what we did, and we are some ongoing projects to extend these results and maybe to apply these results to certain other moduli problems. But yeah, we'll see. Maybe it's a good time to stop, so I will stop here. Thank you.
Okay, thank you, Ilker. Okay, any questions?
Yeah, this is a generalization of symplectic geometry. Not really, not really. So what one can introduce, I mean, there are cases, kind of sheaf theoretic way of writing Riemannian structure over some, let's say, Z-graded manifolds or something like this. But for arbitrary derived stacks, not done yet. So introducing shifted metric structure on a derived stack, okay, and proving usual Riemannian geometric identities. This is a new paper. Okay. And also complex structure. What's the meaning of shifted complex structure? It's another. Of course, you need some motivation. I mean, people did this because of this, applications of symplectic geometry to certain moduli problems, quantization business. So therefore, they have nice examples of applications to certain moduli problems. So yeah.
How much of this thing do you need K to be characteristic zero?
In that paper, they always assume K as a characteristic zero, and also algebraically close. Algebraically close and characteristic zero. Yeah, in that example and the papers I just mentioned, they assume at the beginning, so we are working with characteristic zero.